Hello everybody. Today we're going to be looking at quite literally nothing. So let's actually get right into it. As you can see here today, the problem is quite simple. We have 0 factorial. And before we actually evaluate this, I'm sure a lot of you know what this is equal to, but we're going to be looking at what the factorial even means. So real quick, in algebra and pre-calculus, we're often taught that the factorial is just multiplying a sequence of numbers. So for example, if you have 3 factorial, you may know that this is just 3 times 2 times 1. So we're taught that we just reduce each number by 1 until we hit 1, and then we multiply all this out, and we get 6, for example. Then if we do 1 factorial, or even if I do like 5 factorial, this is equal to 5 times 4 times 3 times 2 times 1. So this is equal to 20 times 6, for example, which is equal to 120. So that's 5 factorial. So the property of the factorial is if we have any number n, and we do n factorial, we define this in our heads to be at least n times n minus 1 factorial. So if we look at, if we plug in any number for this, let's see what happens. Let's say we have 8 factorial. We're saying that this is equal to 8 times 8 minus 1 factorial. And indeed it is, because of our earlier definition, we had 8 factorial is equal to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, like this. This is just 7 factorial into itself. So we have 8 factorial is equal to 8 times 7 factorial, which is exactly what this says. But the issue arises, and I'm sure you can see the issue here. How do we extend factorials into something that is not an integer, or necessarily it's not positive, or it's not negative? Which leads us to today's problem of 0 factorial. Essentially, the factorial function has a lot of background, and many mathematicians have been studying it for centuries, but it even has a physical representation and meaning of it. So factorial wise, let's say we look at 3 factorial. Really simple problem. So let's take an example. Let's say Bobby, this is what Bobby looks like. Bobby's quite happy. He has 3 different boxes, just like this. Let's label this box A, box B, and box C. We're going to be seeing a visual representation of 3 factorial. The question is, how many ways can Bobby rearrange these 3 different blocks into different orders and store them as each permutation? So, for example, what I mean is a valid configuration of these 3 boxes would be A, B, C. That's a valid one. Now, what if I had B in front of A? I can certainly do that. So I could have B, A, C. I could flip this around more, and you can all do this entire thing out. But it turns out there are exactly just like this. Well, let me make sure I got all of them. We got this. I think that's all of them. Yep. So if you can count this up, you'll notice that there are exactly 6 ways for Bobby to organize these 3 different boxes in unique ways where order does matter. If order doesn't matter, then there's only one way he can do it, A, B, C. But yeah, so if you look at it, 3 factorial is actually equal to 6. But is this just a coincidence, or is there some correlation? Well, there are 3 boxes, and that 3 comes in there, and there are 6 different ways. Let's explore. So if we have A, B, and C, if I put this all in a set or whatever you can do it, you don't have to do it mathematically and all. I could say this is S. The thing is, Bobby has initially 3 choices of what the first box may be. So of these 3 different boxes right here, Bobby can choose any one of these 3. So to solve for the number of permutations, we multiply by 3 in the beginning. Now, let's say Bobby chooses some abstract box that we're just going to cross out. We don't know which one he chose, but we have to assume that he did choose one. That leaves us with 2 other options, B and C. It could have been A and C. It could have been A and B. We don't know. But because he has 2 more options, we multiply by 2 because there are 2 distinct ways for each of these scenarios that he could go. There's one route he could take this, or there's one route he could have taken C. So we have to count for that. Now, once he takes one of these boxes, it could be either B or C. I don't know which one it was. There's only one he can choose, no matter what, in both scenarios. So he must choose one. So in this scenario, this gives us 6 different permutations because of the options that he had at each given moment and the decisions he could have made. So this gives us the visual or physical understanding of what the factorial even means. You can pause the video at any time. So of course you can extrude this definition into even cooler things as well. There's all sorts of things, even probability. There's I'm sure you've learned like formulas and factorial all over stuff like that. But for today's problem, we're going to be looking at 0 factorial, and I'm sure you're quite excited. So if you didn't know already, there is a definition of the factorial that extends it beyond just integers and also into the negative sort of realm. It's called the gamma function, and personally, I think it's one of the coolest called functions, gamma functions. It reminds me of gamma rays, which are also really powerful. The gamma function is defined as the following. We usually say it's gamma of z, but we can technically use anything. Gamma of z is equal to the integral from 0 to infinity of t to the z minus 1 times e to the negative t dt. And the specification is that z must be greater than 0, except there are some ways you can extrude this definition even farther, but for the purposes of this, we're going to be saying z is greater than equal to 0. So we're going to add a caveat right there. So essentially, the gamma function, if we really boil it down, the coolest way you can say this is probably it's the area under the curve of this function from 0 to infinity given a value z plugged in here, where t is the variable with you're taking the integral with respect to. So the definition is quite fancy, and if you don't have a basic understanding of calculus, I strongly suggest that you watch some other videos or brush up on that, and I can also make a series on it, so let me know. But if you don't remember, the integral, quite simply, is just the area under a curve. If I have any curve with bounds a and b, it's just the area under it. And this is saying the area from 0 to infinity of this function. And you'll see the other variable. That variable comes from right here. So this allows us to extend the factorial function to even decimal numbers. But for the purposes of this video, to find 0 factorial, let's plug in 0. It's really that simple. So a little thing with the gamma function, it's a very common issue. People will commonly just plug in this number into z, but that's not quite how it works. The way it goes is that if I want to find the factorial of n, this is equal to the gamma of n plus 1. So I have to add 1 when I'm plugging it into the gamma function. Because the gamma function, this entire thing is equal to n minus 1 factorial. That's what it is. So with this definition in mind, let's plug in for 1. So 0 factorial is equal to gamma. I keep writing f because I'm so used to it. Gamma of 0 plus 1, which is equal to gamma of 1, of course. Gamma of 1, which is equal to, now every time we see z, we have to substitute it in for 1. Now we get 0 factorial is equal to gamma of 1, which is equal to the integral from 0 to infinity of, we have t to the 1 minus 1 times e to the negative t dt, which is all equal to 1 minus 1 factorial equals 0 factorial. So this all checks out. Now, here's the fun thing. We'll notice that t to the 1 minus 1, this is actually just t to the 0, and this is equal to 1. So we can completely ignore this right here. Now let's analyze what we have. If we say we have to find 0 factorial, this is now equal to the integral from 0 to infinity of e to the negative t dt. Let's say u is equal to negative t. Then we can say du is equal to negative dt, and then we can solve for dt. Negative du is equal to dt. So we can say, ladies and gentlemen, 0 factorial is equal to, this is going to be negative e to the negative t, all bounded by 0 to infinity. So how are we going to solve this now? The key to doing this problem is just the limits. So to find this from 0 to infinity, we can say on the left-hand side, 0 factorial is equal to the limit as t approaches infinity of, I can move the negative outside, 1 over e to the t, because we have e to the negative t, and this is all minus minus parentheses negative e to the 0. Simply like that. That means 0 factorial is equal to, how do we solve this limit? Simple. When we as t grows larger and larger, this denominator keeps going up and up and up and up and up. As the denominator gets higher, that means the entire fraction of gets closer and closer to 0. So this entire thing right here all becomes 0, and negative 0 is equal to 0. So we have 0 factorial equals 0. This entire thing translates to 0. Not the negative. But then this is minus. The minus still carries. What is e to the 0? Anything to the 0th power, except for 0. I can do a separate video on 0 to the 0. It's a really fun one. Anything to the 0th power is just 1. So we have minus right here, negative 1. Ladies and gentlemen, that means 0 factorial is just equal to 1. And we've achieved our answer. So in summary, we just use the gamma function, which is a really, really handy function for even later mathematics, and seen how we could apply this and get a definition for 0 factorial, and we solve it using some basic calculus. We use a limit here, and then we get 0 factorial equals 1. Now, you could really stop there, and there's really no limits to the gamma function because it's such a cool aspect of mathematics. But the cool part about 0 factorial equaling 1 is that it makes sense too in the physical world. What does it even mean? I had an instructor tell me this once because I asked him, what does it mean for 0 factorial to be 1? Essentially, we said in our earlier example of Bobby, like this, he had 3 blocks. Oh, that's a pretty bad block, but A, B, and C. We asked him, how many ways can you arrange these 3 different blocks? The answer was 3 factorial. So similarly, when we take this definition to 0 factorial, if we have 0 blocks, if I call this A, and we have none of these, we have 0 of these, how many ways can you arrange nothing? Let's say you have, this is the entire space where Bobby is. He has absolutely nothing in the room except for himself. How many ways can you arrange nothing? Exactly 1. And that's how math proves it as well. Such a cool way of extruding this to a physical definition as well. But yeah, it makes sense. The only way to arrange something is you can only do it one way. There's how many other ways can you arrange nothing? So yeah, that's the answer to 0 factorial. It's equal to 1. I hope you guys enjoyed this video. Let me know if you guys have some other different math problems you want me to solve. Leave it in the comments below. Feel free to reach out. But yeah, thank you so much. See you guys.